In this course, we will get to know about expansion modules of MPLC. I will walk you through some of the features of the expansion modules, including calibration and instructions like function 115 dBUF, function 99 TPCTL2, function 38 PID2, function 258 mod configuration, and function 56 CMCTL. Please be noted that we will be using the following tools particularly in this course. MPLC Programming Tool, Upper Logic, at version 0.11.5, MHCM55 at version 1.0.52. You could obtain the latest version of Upper Logic by accessing the FATEC official website. In this section, we will introduce the following key knowledges. Essential features of expansion modules. Must-know number regarding expansion modules. Configuration of expansion modules. Runtime monitoring and control of expansion modules. Some essential features as follows. Jointly well integrate expansion modules with MPLC, and we will go through them one by one. FATEC Hyperbus maximize the communication speed between PLC and modules. The great processing capability of modules help offload the CPU unit from functions, like PID, scaling, alarms, etc., to a great extent. And even with multiple PID instructions operating simultaneously, this design of distribution computation provides an almost constant execution time of PLC. MPLC provides input and output signal range configuration, through which field engineers can use software configuration to complete the signal range setup, instead of doing hardware adjustment like FBs/B1 series. MPLC can support up to 64 expansion modules, 6 of which can be high-speed expansion modules, 2048 points of which can be digital inputs or outputs, 256 channels of which can be analog inputs or outputs, and 14 ports of which can be serial ones, adding up to built-in RS-485S of the CPU unit. We will go through the following key knowledges in this section regarding the configuration of expansion modules. Besides being mentioned earlier, Device View also serves the entrance of setting up expansion modules. Double-clicking on the selected module displays the configuration window, where device information gives the model name and the module ID, and further information can be seen during connection, including firmware and hardware, version, and serial number as well. In this practice, we will know about the procedure of doing a firmware update on MHCM55. Here I have a Mi 3C6-1616T equipped with a MHCM55. First, let's create a new project. Add a MHCM55 on the device view. Change connection mode as online monitoring or online editing mode. Double-click the MHCM55 on the device view. In order to make this work, make sure the firmware version of the module is under version 1.0.52. Confirm and click to upgrade. Select the firmware file to upgrade to. Hit the upgrade button. Wait for completion and check the version. Configuration settings display the corresponding settings of a module. While downloading the project, one can select the modules to download to. In this picture, R0 means this module is located at the first position on the right side. Automatically allocated device memory of a module can be monitored through Device Monitor, including DI and Do area, IR and or area, SR area, and SM area, which saves time of search and creating status pages. The top of the information window lists 4 areas of monitoring. Here we select D, which stands for DI or do, and we can observe that one can monitor the status of X16, X31, and Y16, Y31 of M16, 16, XYT in this way. Here we select A, which stands for IR or, and we can observe that one can monitor the value of R34768, R34771 of M04AD in this way. Here we select S, which stands for SR, and we can observe that one can monitor the value of R35872, R35885 of M04AD in this way. Here we select M, which stands for SM, and we can observe that one can monitor the status of M9199, M9246 of M04AD in this way. Some of the expansion modules require calibration, which has been done during production though. Calibration aims to reduce or eliminate inaccurate measurements, which can be performed by software or registers. Take the load call module for example. The calibration function is listed at the end of the configuration settings, which provides a step-by-step way to guide users through the process of calibration. Some of the expansion modules provide a way of calibration by registers, which is suitable for situation where on-site calibration is required and HMI can be used in the application. This data buffer function will be activated and controlled through relays. The collected data will be stored in the data buffer area set up by this instruction, so one can observe the trend of the digital operation values for a stint. The definition of function 115. ID is the module index. CH specifies the channel index. D is the base register of collected and retrieved buffer data. Here is the video demonstration of how to use function 115 dbuf. In this video, we output 010V from M04DA to M04AD, and the operating value is mapped to 0100. In the program, every 0.01 seconds M04DA increases the output voltage by 0.1 V, starting from 0 V. When the output voltage reaches 10 V, it then decreases the output voltage by 0.1 V. The whole process of the variation of output voltage will then be repeated constantly. Function 115 should be working with relays allocated for the M04AD to perform the function. Enable the data buffer request relay to start the buffering. Enable the data buffer trigger relay to start the collection. According to the configuration, FUN115 saves 200 channels of data before and 400 channels of data after the trigger relay is set on. That makes a total of 600 channels of data. We then can observe that in the status page, our 3000, our 3599 shows all of the collected data. Function 99 TPCTL2 is improved from the legacy function 86 TPCTL in the FBs, which provides additional auto-tuning and incremental PID mode, and cooperate with the design of distribution computing to achieve high efficiency of PID control. The definition of function 99 is very much similar to function 86 TPCTL, but one should dive into the parameter for further understanding, which can be referred to in the PLC instruction manual. Here is the video demonstration of function 99 TPCTL2. In this video, we use M04DA to simulate the source of temperature. M04TC is configured as K-type and PID enabled. All the register to be monitored are listed on the status page, including SR, PR, OR, and WR. First, we start the auto-tuning process of function 99. The triangular curve shown in the monitored waveform shows the process of auto-tuning. After completion of auto-tuning, Kp and T are generated and put in the corresponding registers. The PID control, which is then performed based on KP and T, demonstrates a smooth control procedure constantly afterwards. Function 38 PID2 is an improved version of Function 30 PID of FBs, which also adds auto-tuning and incremental PID mode, and cooperate with the design of distribution computing to provide generic PID control. The added incremental mode of PID can be used for applications like motor control, different from the absolute mode. In this mode, the output varies based on the previous result, meaning that the output will not be minimum once reaching the set value, like for temperature control, which is not suitable for an application like motor control, where minimum output causes stop. One could dive into the parameter for further understanding of Function 38, which can be referred to in the MPLC instruction manual. Here is the video demonstration of Function 38 PID2. In this video, we use M04DA to output 010V to M04AD to simulate analog inputs. We set the PID method as 3 for operating in incremental mode. All of the registers of Function 38 are listed on the status page, including SR, or PR, and WR. Start the procedure of Function 38. We can see a smooth PID control. Function 258 tare sub subtracts the tare weight from a given channel on the LC unit. One touch mode. Regard the current weight as tare 1 and subtract it. Digital mode. Subtract the designated tare weight value. Function 258 is a type of instruction dedicated to be used with expansion modules. The definition of the instruction can vary depending on the selected OP mode. For a load cell module, two modes of tare subtraction are provided. When the OP is set as tare sub, RST is used to reset the tare weight, and SB specifies the tare weight to subtract from. Here is the video demonstration of function 258 modconf tare sub. Let's start with digital mode, and we subtract the designated tare weight from the measured result. The measured result is 2.2 kilograms. The value of tare weight to subtract is 10, with unit of 0.1 kilograms. After starting function 258, we can get 1.2 kilograms then, which is the result of subtracting 1 kilogram from 2.2 kilograms as planned. Digital mode is applicable in applications where the weight of the container is known and fixed. Next up is the one-touch mode, and we treat the current weight as the tare and subtract it. The measured result is 2.2 kilograms still. After starting function 258, the tare weight now is considered as 2.2 kg, so we get 0 kilograms here. One-touch mode is suitable for applications where the weight of the container is variant or not unknown in advance. Tare zero offset function aims to remove tare weight as well. It's just that it performs the zero operation at hardware level as to obtain a possible higher resolution of weight value. Auto-adjusting mode. The corresponding parameters are automatically calculated. Manual adjusting mode. The corresponding parameters are given by users. Auto-adjusting mode is recommended most of the time. Here is the definition of function 258 TARES ROFFSET. MD assigns auto or manual mode. WR is where relevant parameters are filled in. Here is the video demonstration of function 258 modconf tares ROFFSET. We use auto adjusting mode in this video. The measured result is 2.2 kilograms. After starting function 258, the measured 2.2 kilograms is considered as the tare weight and got removed, resulting in 0 kilograms. All three parameters of WR are filled in automatically generated gain values. Function 156 CMCTL is a communication instruction for CM22/CM25/CM55 units. The design concept is based on synchronous/asynchronous communication methods, such as SDO/PDO of CA-NOPN protocol, running independently from CPU unit most of the time. Supported functions include Modbus RTU/ASCII master/slave, as well as UD send/send and receive, and send. Function 156 CMCTL does not need editing of communication tables, but requires proper settings of configuration accordingly. Two other key points to set up is TS and MD of Fun 156 to be able to enable communication successfully. In the following practice, we use MHCM55 as an example. We send out D0D9 from port A to R0R9 of port B using user-defined protocol, and afterwards we reply R0R9 from port B to D10D19 of port A, completing a loopback example. Port A is configured as user send. Port B is configured as user receive. Baud settings are configured the same. Two user-defined packets are created for port A, both of which are starting with SDX and ending with ETX. One is related to D0D9, and the other is related to D10D19. Here we add a new communication entry to port A. The packet mode is set as send and receive, and we configure the RX and TX packets accordingly. For port B, we create a user-defined packet, starting with SDX and ending with ETX. This one is related to R0R9. Here we add a new communication entry to port B. The packet mode is set as receive and send, and we configure the RX and TX packets accordingly. Now all the settings are complete. We use two function 156 for port A and port B individually. Both of them start with table number 0 and run in cycles. Now, we will implement the practice of user-defined send and receive. First, prepare a ME3C6-1616T and MHCM55, and then create a new project. Add a MHCM55 on the device view. Double-click the MHCM55 on the device view. Configure the MHCM55 accordingly. Port A is configured as user send. Port B is configured as user receive. Baud settings are configured the same. Two user-defined packets are created for port A, both of which are starting with SDX and ending with ETX. One is related to D0D9, and the other is related to D10D19. Here we add a new communication entry to port A. The packet mode is set as send and receive, and we configure the RX and TX packets accordingly. For port B, we create a user-defined packet, starting with SDX and ending with ETX. This one is related to our 0R9. Here we add a new communication entry to port B. The packet mode is set as receive and send, and we configure the RX and TX packets accordingly. Now all the settings are complete. We use two function 156 for port A and port B individually. Both of them start with table number 0 and run in cycles. Download the project and run the PLC. Enable both function 156. Change the value of D0, D9, and observe R0, R9, and D10, D19. Please feel free to ask any question or make any suggestion to the local FATEC distributors worldwide, or leave a message on the website.